All right, we are looking at 12.2 today, inference for two-way tables. So some learning targets. We talked about the chi-square test for goodness of fit in 12.1. Today we're really looking at two other chi-square tests, one titled homogeneity and the other is independence. And we'll kind of take a look at that. But here are the learning targets if you want to look at them, but we'll continue on. So this is a question that we're going to explore. Does background music influence what consumers buy? One experiment in a European restaurant compared three randomly assigned treatments: no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entrees. So our two hypotheses are our null hypothesis is there is no difference in the true distribution of entree orders at this restaurant when no music, French accordion music, or Italian string music is played. And the alternative is there is a difference in the true distribution of entrees ordered at the restaurant. Now, the big difference here is that typically our null hypothesis was always there. They were kind of flip flopped. We assume that these things were well, the wording's a little flip-flopped. We assume that things were always equal, and that's actually what we're kind of doing here. But the word "no" is what pops up in H naught, which is a little bit new. Normally we say does not equal for our alternative, so that word "no" or "not" usually falls in the alternative, but here it actually falls in the null, and that should make sense um, because as I wrote it down here, we normally say two things are equal, or in this case, a couple things are equal or the same. And since we're testing for homogeneity, right, that root word homo means same. So we assume there are the same or there's no difference. No difference would mean they're the same. Okay. So that's kind of a little way to kind of remember, hey, this is the really the first time we're seeing our null hypothesis have the word no in it. So here's some data that we're given, and it's positioned in a two-way table. So we have the type of background music at the top, and then the entree ordered. And these are some graphs we could make. So just based on this data, if there's no music, this is the percentage of each type of entree, and so forth. So you can see there's kind of it looks like there's a difference. And with hypotheses testing, we always try to see, hey, how big of a difference is that? How strong of a difference is this case here? And is it statistically significant? So that's the question we're going to answer. And is this actually significant, or does this just happen by random assignment of the treatments? So we could compare many pairs of properties ending up with many tests and many p-vals. So like we could compare no music to French, and then do another test, do no music to Italian, do another test, French to Italian, and kind of see if there's changes there. But that's a lot of tests to do, and it's not a good idea. And it's actually one way that you can increase the probability of making a type 1 error for one of those tests. So you really don't want to make a type 1 error. Um, so we want to stay away from that. So the problem of how to do many comparisons at once without increasing the overall probability is kind of common, and it's two steps to do. First, we're going to perform an overall test to see if there's any evidence. And then if there is evidence, you would do specific tests to see what that evidence actually is. It's a little similar to what we talked about in the goodness of fit. We saw, hey, there was statistical evidence, and then we kind of just looked at, in that case, um, where that evidence was coming from, what was really leading to that conclusion that we made. It's kind of similar to here, except here we might actually do a whole nother test. In the homogeneity, we didn't do a whole nother test. So to find the expected counts, we start by assuming H naught is true. And remember, H naught is there is no difference. Okay. So if the specific type of music that playing has no effect on entree order, the proportion of French entrees ordered under each music condition should be 99 out of 243 because that's how many total people ordered French entrees. And because there's a total of 84 total entrees ordered with no music was playing, we would expect 84 times the 99 divided by 243, or 34.22 of those entrees to be French on average. So the fact that, hey, on average, we'd expect 99 out of 243. This is a probability of selecting a French entree. And since there is no difference, then we would expect that that would hold for all types of music. So 84, if there's 84 um, total entrees ordered when no music was playing, we would expect 84 times that number to be the number of French entrees. So you could replace that whole situation with, or you could do that over and over and over again to kind of fill in this expected counts. Um, One way is this formula is pretty useful, I believe, because it's the expected count equals the row total. So row total 99 times the column total 84 divided by the total 243, and that would go in here. If I wanted this number 30.56, it's going to be the row total, which is 99 times the column total 75 divided by total 240. Easy. 30.56. That's how they got that. And this is just a little color coding. So row total is this number, column total is here, table total is here, and the answer would go in that category. So as a chi-square test for goodness of fit, the expected count should not be rounded to the nearest whole number, while an observed count of entree orders must be a whole number, and expected count need not be a whole number. The expected count gives the average number of entrees ordered if H naught is true, and the random assignment process is repeated many times. So, like before, chi-squared, the number, or how to get that value of chi-squared, that's the statistic that we're going to use. It's when you take the observed count minus the expected, square it, divide by the expected, and add those all up together. So the sum is over all cells, not including the totals in a two-way table. So in this case, you see a couple of the examples, and remember when you're doing this, you can do the first plus the second plus ... plus the last. That shows sufficient work. Just giving me 18.28 does not give me sufficient work. This is the work you need to show in order to get full credit. All right. And that's exactly what this AP exam test says. Let's take this, let's do an actual test of this with a little bit different information. So problem, for a class project, Abby and Mia want to know if the gender of an interviewer could affect their responses to a survey question. The subjects in the experiment were 100 males from their school. Half of the males were randomly assigned to be asked, would you vote for a female president by a female interviewer? The other half of the males were asked the same question by a male interviewer. The table shows the results. State, okay, and then part three, part A, B, and C. So part A, state the appropriate null and alternative hypothesis. So remember, our null has that word not in it. There's no difference. Our alternative is there is a difference. So H naught, there is no difference in the true distributions of response to this question when asked by a male interviewer and when asked by a female interviewer for subjects like these. And then HA is very similar, but there is a difference in the true distribution of responses to this question when asked by a male interviewer and when asked by a female interviewer. Ooh, expected counts. Remember, expected counts it would be row total times column total divided by table total. So 69 times 50 divided by 100 would go up here, and that's how I got 34. 69 times 50 100. So I got 34.5. Okay. And then you can do the same thing for the rest of the table. If I wanted to add them up, I would do the observed minus the expected squared divided by the expected, and show that work for the first, the second, plus dot 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 plus the last one. And I get my chi-squared value to be 4.25. All right, our conditions exactly the same as the test for goodness of fit. All right, the one new thing, like we said in 12.1, large counts are all must be at least 5. So here's my observed counts. Here's my expected, and it's just kind of go through step A, B, and C. So verify the conditions for inference are met. Well, we know there's a random sample of 100 people, and then all expected counts are larger than 5. And you can write the C table for expected counts, but you better have the expected counts written somewhere. You cannot just say, oh yes, every number is greater than 5. You must show each individual number and tell me that they are all larger than 5, or you will lose points. All right. We do not need to check the 10% condition because Abby and Mia didn't randomly select subjects from some population. This was technically an experiment because they put you in 2 groups depending on who's asking you the question. So let's use table C to find the p-val, then use your calculator's chi-square to find the CDF command. This is a new thing of the degrees of freedom, and we'll talk about it a little bit later, but degrees of freedom for this is the number of rows minus 1, so 3 minus 1, times the number of columns, 2 minus 1. We do not include the total rows in column as one of our rows in column. Okay, so here, 3 minus 1 times 2 minus 1 would be 2. If I use the table C, I could find it, but if I use technology, chi-squared CDF 4.25 comma 10,000 comma 2 get 0.119. So the same that they get. All right. And we calculated that chi-squared statistic is 4.25. It wants to interpret the p-val from our calculator. So our p-val is this number right here. So remember, within any hypothesis testing, we're assuming H not to be true. So assuming the gender of the interviewer doesn't affect responses to this question, there is a 0.119 probability of observing differences in the distribution of responses as large as or larger than those in this study by chance alone. And the definition of p-val again. Now they ask what conclusion you would draw, and this is where all of our first sentences should be almost identical. Because or since the p-val is 0.119 is greater than alpha, which is 0.05, we fail to reject H naught. There is not convincing evidence of a difference in the true distribution of responses to this question when asked by a male interviewer and when asked by a female interviewer. So we fail to reject H naught, so there's not convincing evidence of a difference. Or we say there's not convincing evidence of HA. All right, this is the next subsection, and then other type of test that might come up. It's called the test for homogeneity. Actually, I think we're still on this. Is this where we're at? Yeah, sorry. Didn't get to the new test yet. But as usual, technology saves us time. and gets the arithmetic right. So you can actually put your data into matrices. Um, if you forgot how to do that or didn't learn how to do that, that's okay. We'll go to second matrix. When we do second matrix, this is if you click to enter here, it would just use matrix 1. All right, let's go second matrix back. So that's how you use it. The second column is a bunch of math options. The first one's probably the most common with the determinant. But if you want to edit and put your data in, like you edit your list, you table all the way over, press enter. And now you get to choose up at the top, what size do you want? So it always goes row by column. So 3 rows, here I have 3 rows by 5. I'm going to change it back down to 3 rows by 2. I'm using the data that we had from, what is it, this example. This example here, and render that male and female one. So I have my observed count here, and then I'm going to go second matrix over to edit, edit 2, and I have my expected counts here. So now when I do my test, it goes stat test down, down, chi-squared test. And if you saw me try this on for 12.1, I made a mistake. It, for some reason, wasn't working, but this will work here. So I have my observed in A and my expected in B. All right, I'm going to calculate, press enter, boom, I get the same information, 0.1196. Even my degrees of freedom come up as 2, and my chi-squared is 4.25. So I just want to show you how to do that really quick. And so we're going to fly through these couple slides. Like we talked about this all year, use your calculator to carry out the mechanics of a significance test, but you need to clearly state everything, okay? Make sure not just this, but you state the name of the test, the chi-squared value, the degrees of freedom, and the p-value. That's bare minimum, and that still might not get you full credit, okay? You need to show your work. How'd you get this number? In this case, it's really easy. Do the first plus the second plus dot, 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 plus the last term, and go from there. So, problem, do these data provide convincing evidence at the alpha 0.05 level that the distribution of opinions about speaking English differ for residents of Australia, the UK, and the US? So, remember, if it asks us if this data provides convincing evidence, it's telling us to do the fourth process and do the whole hypothesis testing. So I want you to take a short break, well, not a break, but kind of do this problem on your own and then come back to this video. So I'll give you a second to kind of work on this first question alone. Remember, in your state phase, you really need your hypotheses and your alpha value. All right, so hopefully you got that done. We'll look at it here. So my H naught is there's no difference in the true distribution of opinions about speaking English for residents of Australia, the UK, and the US. And then HA is obviously there is a difference. And we're using alpha 0.05. In my plan, I have independent random samples of residents from the 3 countries. My 10% rule, 1,000 is less than 10% of all Australian residents. 14, and I'm using these totals here. 1460 is less than 10% of all UK residents, and 1,003 is less than 10% of all US residents. The large counts, we do have to do a little bit more work to get our expected values, but remember it would be 2569 times 1,000 divided by 3463 to go in this category right here. So if I did that, I can show all my expected counts and boom, get that here. Let's just double check for you all. 2, 5, 1. Boom, 741.8. So just so you know how you know. And then you check each one of these and they are all greater than 5, so we're good to go. And from there, we do the do phase. So I'll go back, give you a second, give you a chance to do the do phase. All right. So in the do phase to calculate that chi-squared, right, you're going to do the observed minus expected divided by expected. So they do first plus the second plus dot dot dot. I would honestly still show plus the third, or plus the last one, just to be on the safe side, but I guess they're okay here. The degrees of freedom, again, is the amount of rows minus 1 times the amount of columns minus 1. So 4 minus 1 times 3 minus 1 is 6. And 68.57, that's really far to the right. So this is going to be a very small probability, and it comes out to about less than 0, approximately 0. So what conclusion are we going to make? Well, because our p-val of approximately 0 is less than alpha, we reject H0. There is convincing evidence that there is a difference in the true distributions of opinion about speaking English for residents in Australia, the UK, and the US. All right, the next type of test, which will come off, is called the test for independence. And so this is a kind of topic question. Are people who are prone to sudden anger more likely to develop heart disease? An observational study followed a random sample of 8,400 people with normal blood pressure for about 4 years. Each person took a test. Research also recorded when each individual developed coronary heart disease. So take this data, put it into a boxed chart. Not a terrible idea. We might lose some of the specific values or exactly how much they make, but overall, it's not a bad idea. So the question is, do these data provide convincing evidence of an association between the variables in the larger population? Well, whenever there's that question, that again, do the data provide convincing evidence? That is a cue to do a hypothesis testing. So my alternative, or my null is there's no association between anger level and heart disease. My HA is there is an association between anger level and heart disease. Another way to write the equivalent is, here you go below, but I'm not going to read that for you. But if you want, you can pause it. So let's get through testing. So we did the state phase. We're now on the plan. So the big thing we're going to need is we're going to need all those expected counts. So if we imagine choosing one of these people at random, the probability of yes is 190 divided by 8474. Now the big thing is, since we're assuming this PS to be true, PES given low wage. So, well, if it's true, that means that they're independent, right? There is no relationship, no association. That means these are independent. And if things are independent, well, then the probability of yes given anything, if that anything is independent to yes, it's going to equal just probability of yes. That is one of our definitions of independence events, but just to remind us there. So 190 divided by 8474 is this number there. To find the expected counts up here, I would times it by that row column. I get my expected count to be 69.73. And here is a snapshot of said two-way table. So expected counts, just like before, row total times column total divided by table total. The three conditions are exactly the same as before. Random sample, Sampling without replacement, your sample size has to be less than 10%, and all expected counts must be at least 5. This picture should look very similar to the most recent one for the test of homogeneity. Same idea here. Same way to find your degrees of freedom as well. Timeout. All right, back together. So we have this problem. In chapter 1, you read about a random sample of winter visitors to Yellowstone National Park. Each of the 1,526 visitors in the sample was asked 2 questions. Do you belong to Environmental Club? And what is your experience with the snowmobile? Own, rent, or never used? And there's the two-way table from it. So do these data provide convincing evidence of an association between environmental club status, and type of snowmobile used in the population of winter visitors to Yellowstone National Park. So again, we're going to do a test here, a significance test. So starting off with our hypotheses. So they're going to be very similar to before. There is no association between environmental club status and type of snowmobile used in the population of winter visitors. And then the HA is there is an association. Okay. And we'll use alpha zero point 0.5 here again. So our plan is we're going to do a chi-square test for independence, and then random sample, good there, 10%. It's reasonable to assume that 1,526 is less than 10% of all winter visitors to Yellowstone. And then large counts, we are going to have to do those. But remember, large counts would be 657 times 1221 divided by 1526, and that number would go in this category, this box right here. If you did all of them and they're all greater than 5, then we're good to go. So see, and voila, they are all bigger than 5, so we are good to proceed. I do want to go back a second. Notice how they still said large counts. All expected counts are at least 5. See table below. You need both. You need the statement that they're all larger than 5, and you need to actually show that, hey, they really are all larger than 5. You can't just make that number up. For chi-squared, that number, we can calculate it using our expected and our observed. Our degrees of freedom, same thing as before. It's going to be 3 minus 1 because there's 3 rows, and columns there's 2, so 2 minus 1. And then you could do the test. And let's see if we did it on here. It's obviously it's going to be very, very small. Ooh, I'm not going to put it all in there, but you could do it. And you get a very small number. And since it's so small, our p-value is approximately 0, which is less than alpha, which is 0.05. We reject H naught. And we have convincing evidence of an association between the environmental club status and the type of snowmobile used. Just a reminder for some people, when p-value is very small, the calculator will report it using scientific notation. Remember, the p-values are probabilities and must be between 0 and 1. Right. So the question is when to use chi-square test for homogeneity and when to use chi-square test for independence. So the best way to distinguish the two are tests. The two tests is to consider how the data were produced. So if the data comes from 2 or more independent random samples or treatment groups, so if it's an experiment with multiple groups in a randomized experiment, then do a chi-square test for homogeneity. Right? Because you're going to see if these groups are the same or not. If the data comes from a single random sample with the individuals classified according to 2 categorical variables, use a chi-square test for independence. Okay, so this is the kind of red light here that you want to make sure you have this down so you know which type of test to use. So, are men and women equally likely to suffer lingering fear from watching scary movies as children? Researchers asked a random sample of 100 a random sample of 117 college students to write narrative accounts of their exposure to scary movies before the age of 13. Blah, blah. Assuming the conditions for performing inferences are met, many tab has the data below. And it says, should a chi-square test for independence or a chi-square test of homogeneity be used in this setting? Well, we have one sample of 117 college students, so it should be a test for independence because it's one sample. That homogeneity, remember, you're trying to see if the things are the same, and you're really seeing, hey, are these different populations the same? So that's kind of one way you can remember the independence. Right. The next question is state the appropriate pair of hypotheses then. So this is for independence. So there is no association or there is an association. So it's not, there is no association between gender and whether or not college students have lingering fright symptoms. And then HA, there is an association between gender and whether or not college students have lingering fright symptoms. So what cell contributes the most to the chi-square test statistic? In what way does the cell differ from the null hypothesis suggest? So this is where you're going to really want to examine this null hypothesis, or not the null hypothesis, the mini-type outlet. So you know you're doing a chi-square test for independence, okay? And so that means that you have a two-way table. So you're going to have some row of totals, which we do here, doing totals and totals. So I'm looking at this inner part. It says chi-squared test male versus female. Expected counts are printed below observed counts. So that's observed, expected, observed, expected, observed, expected, observed, expected. All right, so now what's this bottom row? 1.883, 0.906, and then 0.837 and 0.40. Well, those are actually the numbers that correspond to your chi-squared number. All right. If you didn't know that, you could take the observed minus the expected and do that whole formula that we've been doing, squaring that, dividing it, and then adding them all together. And you can tell what's the observed and what's the expected because it's in words, but also the observed must be whole numbers while the expected could be a decimal. So the question is which one of these contributes the most? Well, it would be the largest number, which is 1.883. So men who have lingering fright symptoms account for the largest component of the chi-square test statistic. Far fewer men in the sample admit to lingering fright symptoms than we would expect if HO were true. So it says, interpret the p-val. What conclusion do you make? Well, the next thing is, hey, our p-val is right here. Boom, 0.045. So the conclusion you're going to make, well, p-val is greater than alpha, so we're going to fail to reject. But first, we need to interpret the p-val. And the way you interpret the p-val is if there's no association between gender and whether or not college students have lingering fright symptoms, that's basically saying, assuming H naught is true, that's what H naught is, there is a 0.045 probability of obtaining an association as strong or stronger than the one observed in the random sample of 117 students. Right, so it's assuming H naught is true, there is a blank probability of obtaining this number or stronger, right? That chi-squared in this case, or stronger in one observation based on this number. Right, so that's how you interpret your p-val. And then the conclude, like I said, our p-val is 0.045. So because 0.045 is greater than alpha, 0.01, we failed to reject H naught. I think I might have said that backwards earlier. But p-val is greater than alpha, so we failed to reject H naught. We do not have convincing evidence that there's an association between gender and whether or not college students have lingering fright symptoms. Right. And we have made it through 12.2. So here are the learning targets for you. State appropriate hypotheses and compute the expected counts and chi-square test statistics for a chi-square test based on data in a two-way table. State and check the random 10% in large counts condition, which we've done quite a few times today. Calculate the degrees of freedom. Well, I'll tell you. So random and 10% the same. Large counts, that means all expected values must be larger than 5. Calculate the degrees of freedom. That would be the number of rows minus 1 times the number of columns minus 1. But don't use the totals in that number. Then you can use your calculator or the C table to find your p-val based on that chi-squared number and the degrees of freedom. And then the other two are perform a chi-square test for homogeneity. Remember, that's multiple samples, while the test for independence is one sample. All right, and that kind of highlights the last thing. So that is all we have for today.